Variable speed drives, or VSDs, offer a compelling solution for reducing power consumption in domestic water systems. Recent findings highlight the significant energy savings and quick return on investment associated with VSD installations. A survey reveals that installing VSD can drastically cut power usage, often achieving a payback period of less than 14 months. The information gathered from monitoring a 55-story building, which initially consumed over 500,000 kilowatt-hours per year, provides a clear illustration of these benefits. The data collected shows that installing VSD could reduce power consumption by approximately 45%. This substantial reduction translates directly into lower operating costs and improved energy efficiency. Furthermore, the initial investment in VSD installation can be recovered in less than 14 months, making it a financially attractive option. Data loggers were used to project how VSD would maintain consistent system pressure by precisely adjusting pump speed. This adjustment optimizes pump operation, reducing unnecessary run time and minimizing energy wastage. The pumps run at reduced cycles, around 52 cycles instead of the typical 60 cycles. The motor consumes significantly less power compared to running at full speed. These findings are not limited to large buildings. Smaller buildings have demonstrated similar results, further validating the effectiveness of VSD across different scales of operation. Recent increases in fuel surcharges have further amplified the financial benefits of VSD. A 10% increase in power rates due to these surcharges added approximately $5,000 per year to the operating costs of the domestic water system in the 55-story building. This additional expense underscores the importance of implementing energy-efficient solutions like VSD. Contractors can leverage these findings to provide valuable advice to their customers. By informing them about the potential cost savings and improved efficiency of installing VSD in domestic water systems, contractors can help them make informed decisions that benefit both their bottom line and the environment. The benefits of VSD are threefold. Firstly, they reduce power consumption. Secondly, they lower operating costs. And thirdly, they provide a quick return on investment. By understanding these advantages, contractors can effectively communicate the value proposition of VSD and help their customers improve the energy efficiency of their buildings. The existing setup in the 55-story building consists of one 25-horsepower pump, two 50-horsepower pumps supplying the upper floors, and two 30-horsepower pumps supplying the lower floors. With data loggers, the projected total power consumption was estimated to be over 500,000 kilowatt-hours per year. While drive manufacturers often claim savings of up to 2/3, real-world experience suggests that savings of around 45% are more realistic. System pressure is maintained by precisely controlling pump speed using the VSD. In smaller buildings, pumps typically run at around 52 cycles, increasing to 55 or 56 cycles during periods of high water demand. At 52 cycles, the motor horsepower consumption is nearly 50% of its rated capacity. During the study and the 55-story building, power rate increased from 0.68 to 0.76 cents per kilowatt-hour due to fuel surcharges. This increase alone resulted in an additional cost of nearly $5,000 per year to operate the domestic water system. This additional expense provides further justification for investing in energy-efficient solutions such as VSD. Contractors can use this information to present a compelling case for VSD installations to their clients. The technology behind VSD involves several key components working in concert to achieve energy savings and improved system performance. The VSD itself is an electronic device that controls the speed of an alternating current, or AC, induction motor by varying the frequency and voltage supplied to the motor. This control allows the pump to operate at the precise speed required to meet the current demand, rather than running at full speed all the time. The main components of a VSD include firstly, a rectifier, secondly, a DC bus, and thirdly, an inverter. The rectifier converts the incoming AC power to direct current, or DC power. This DC power is then stored in the DC bus, which consists of capacitors that smooth out the voltage and provide a stable power source for the inverter. The inverter converts the DC power back to AC power, but at a variable frequency and voltage. This variable frequency and voltage allows the motor speed to be precisely controlled. The VSD also incorporates sophisticated control algorithms that monitor system pressure and adjust pump speed accordingly. These algorithms typically use feedback from pressure sensors to maintain a constant pressure, regardless of changes in demand. This precise control not only saves energy, but also improves system performance by reducing pressure fluctuations and extending the lifespan of the pumps. The installation process for VSD typically involves several steps. Firstly, the existing motor starter is disconnected and removed. Secondly, the VSD is mounted in a suitable location, typically near the motor. Thirdly, the VSD is wired to the motor and the power supply. Fourthly, pressure sensors are installed in the water system to provide feedback to the VSD. Finally, the VSD is programmed with the appropriate parameters, such as the desired pressure set point and the motor's specifications. Proper installation and programming are essential for ensuring optimal performance and energy savings. There are several factors to consider when selecting a VSD for a specific application. Firstly, the motor horsepower rating must match the VSD capacity. Secondly, the voltage and frequency of the power supply must be compatible with the VSD. Thirdly, the environmental conditions, such as temperature and humidity, must be taken into account. Fourthly, the communication protocol supported by the VSD should be compatible with the building's automation system. It is also important to choose a VSD from a reputable manufacturer that offers reliable products and good technical support. Regular maintenance is essential for ensuring the long-term performance of VSD. This maintenance typically includes, firstly, inspecting the VSD for any signs of damage or wear. Secondly, cleaning the VSD to remove dust and debris. Thirdly, checking the voltage and current levels to ensure they are within the specified limits. Fourthly, testing the VSD functionality to verify that it is operating correctly. It is also important to keep the VSD software up to date to ensure that it has the latest features and bug fixes. The benefits of using VSD extend beyond energy savings. VSD can also improve system reliability by reducing stress on the pumps and motors. By controlling the pump speed, VSD can minimize the occurrence of water hammer, a phenomenon that can damage pipes and fittings. VSD can also extend the lifespan of the pumps and motors by reducing the number of starts and stops. In addition, VSD can provide valuable diagnostic information that can help to identify and prevent potential problems. The technology is not without its limitations. VSD can generate harmonic distortion, which can affect the power quality in the building. Harmonic distortion can cause problems with other electrical equipment, such as transformers and generators. However, harmonic filters can be installed to mitigate this issue. VSD can also be sensitive to voltage fluctuations and power surges. Surge protection devices should be installed to protect the VSD from these events. Finally, VSD can be more expensive than traditional motor starters. However, the energy savings and improved system performance can often offset the higher initial cost. The return on investment for VSD can vary depending on several factors. Firstly, the size of the motor. Secondly, the operating hours. Thirdly, the electricity rates. Fourthly, the incentives offered by local utilities. In general, the larger the motor, the more operating hours, the higher the electricity rates, and the more generous the incentives, the faster the return on investment will be. There are numerous case studies that demonstrate the benefits of VSD in domestic water systems. In one case study, a hospital installed VSD on its water pumps and reduced its energy consumption by 30%. The hospital also experienced a reduction in water hammer and improved system reliability. In another case study, a hotel installed VSD on its water pumps and reduced its energy consumption by 25%. The hotel also experienced a reduction in pump maintenance costs. These case studies provide compelling evidence that VSD can be a valuable investment for building owners. Contractors should stay informed about the latest developments in VSD technology and best practices for installation and maintenance. They should also be aware of the incentives offered by local utilities and government agencies. By providing their customers with accurate and up-to-date information, contractors can help them make informed decisions about VSD and other energy-efficient technologies. The installation of VSD can also contribute to a building's overall sustainability goals. By reducing energy consumption, VSD can help to lower a building's carbon footprint and reduce its impact on the environment. In addition, VSD can help to conserve water by reducing leaks and minimizing water hammer. As sustainability becomes increasingly important, the use of VSD is likely to become more widespread. Contractors who are knowledgeable about VSD will be well positioned to capitalize on this trend. The application of VSD is not limited to domestic water systems. VSD can also be used in a variety of other applications such as heating, ventilation, and air conditioning, or HVAC systems, industrial pumps, and fans. In HVAC systems, VSD can be used to control the speed of fans and pumps, reducing energy consumption and improving comfort. In industrial applications, VSD can be used to control the speed of pumps, fans, and compressors, improving efficiency and reducing maintenance costs. The principles and techniques discussed in this presentation can be applied to these other applications as well. The savings of around 45% observed in the 55-story building are a practical number to keep in mind. Even if the drive manufacturers advertise 2/3 savings, you should be conservative when calculating the savings. When the pumps run at 52 cycles, the horsepower consumed by the motor was near 50%. During this study on the 55-story building, their power rates increased from 0.68 to 0.76 cents per kilowatt-hour due to fuel surcharges. This alone reflected an additional cost of nearly $5,000 per year to operate the domestic water system. This information can give some contractors an idea or two when approaching clients about energy savings.